Okay, today we're going to be introducing matrices. So this is from the Year 1 or AS Further Maths Classification, Core Pure. This is chapter 6, and we're introducing matrices today. So the first question is then, what is a matrix? Well, essentially a matrix is what we call an array of numbers or items. So you might have some algebra kicking around in matrices as well. So for example, we might have the array 2, 3, 0, 1, and that is a matrix. Okay, it's not just a number. It's, in this case, it's 4 numbers, and the numbers in particular positions. The position in each number is specific to that number. And you can have different size matrices. So this is a 2 by 2 matrix because it's got 2 rows and 2 columns. But you might have this matrix: 1, 0, 4, 5, 9, 7. There we go. And this one would be described as a 3 by 2 matrix. So this is a 2 by 2 because it's got 2 rows and 2 columns. This is a 3 by 2 because it's got 3 rows and 2 columns. Be careful not to mix it up with 2 by 3. So a 2 by 3 matrix would be something like this. So I'm going to call it A, B, C, D, E, and F. There we go. So we've got some algebra kicking around now. This one is a 2 by 3 matrix because it has 2 rows and 3 columns. It's the number of rows which is mentioned first. And that's essentially what a matrix is. And today we're going to be looking at how we add matrices together when possible, at how we multiply matrices together when possible. But first, before we move on to all that, let's have a look at a little bit of notation just surrounding matrices. So first of all, you will notice that I have put them all in rounded brackets, and that is common practice for matrices. Okay, you put them in rounded brackets. If you want to define a matrix, you don't have to write out the matrix in full every time. We tend to use capital letters to depict a matrix. So for example, I might say the matrix A is defined as the matrix 1, 2, 3, 4. Okay. And notice I've used a capital A. So if you see capital letters kicking around, it usually means it's a matrix. Okay. But you'll never have a matrix defined as a lowercase. That's just not something that's done. It's not common practice. Each of the numbers inside a matrix is called an element. Okay, so in this case, this here is an element. This here is an element. So in this particular example over here, that matrix A will contain 4 elements, or has 4 elements. As already mentioned, the size of the matrix is, we would denote it generally as n by m. And this means it has n rows and m columns. Okay. You can have something called a square matrix. And this doesn't necessarily mean it's a square number. In this case, a square matrix is a matrix where n equals m. Okay, so it has the same number of rows as columns. This is a square matrix, for example. Okay, it's 2 by 2. Then we have something called the zero matrix. I say the zero matrix. You can actually have whatever zero matrix you want, but a zero matrix is a matrix n by m. Okay, any number of rows by any number of columns where every element is 0. And it's the matrix equivalent of that size of matrix to the number 0. An identity matrix. This has to be square, and it would have 1s down what we call the lead diagonal and 0s everywhere else. And this will become particularly important later on in the course. Okay, we're not actually going to touch on it too much in today's lesson, so we'll come back to that. But it's important to know that identity matrix is a square matrix with 1s down the lead diagonal, which goes from top left to bottom right, and 0s everywhere else. So this, for example, is the 3 by 3 identity matrix, and we could denote that as I3. Okay, I tends to mean the identity matrix, and then I've put a subscript 3 to indicate that it's 3 by 3. Okay, and I'm sure you can use your imaginations as to what I4, I5, I2, or even I1 would look like. Okay, I think that's it for notation. Okay, so on to some addition then. So addition of matrices is fairly straightforward, particularly compared to multiplication of matrices, which we'll get onto in a little bit. But for two matrices to be added together, they must be of the same size. They have to be of the same size. If they're not of the same size, you can't add them together. It's quite simple. So, for example, we have a 2 by 2 matrix here, and we have a 2 by 2 matrix here. Both of those are the same size, so we can add them together. And intuitively, you might be correct as to how you think we would add them together. We just take the element in their respective positions and we add them. So 3 plus 3 is 6. Sorry, so a 6 gets put in. Excuse me, in that top left position, and then we do the same here. So top right, and that'll be a 6 as well because 5 plus 1 is 6. Bottom left, that would be a 10 because 2 plus 8 is 10. And then finally, bottom right, we've got a 0 plus a 1, and that's a 1. And hopefully, just me doing that would emphasize reason enough as to why the matrices would have to be of the same size. Okay, so that would be the answer. This matrix plus this matrix is that. Okay, this one here, well, these are different sizes. So this is a 3 by 2 matrix, and this is a 2 by 2 matrix. So we cannot add them. So you could do the 2 plus the 5, the 4 plus the 2, but the 3, there's no element there to combine with it. Therefore, this doesn't exist. Okay, you can't add half a matrix to one. We just say it doesn't exist. Okay, so it's not possible. And occasionally in exams, you'll see questions which say, where possible, calculate these additions or these multiplications or whatever, and you just need to identify ones that don't exist, or you could just say, not possible to execute, or not possible to do. Of course, in addition to addition, you could subtract, and that's an absolute carry on from what addition is. Again, they have to be the same size, and we just take elements respectively. So in this case, 2 minus 5 is minus 3. 1 minus 5 is minus 4. 4 minus 8 is minus 4. 2 minus 3 is minus 1. 3 minus 1 is 2, and 1 minus 0 is 1. And we can see we've got some negative numbers in the matrix, and that's fine. Okay, negative numbers are completely allowed, as are irrational numbers, fractional numbers, complex numbers, whatever you want. Anything can go into a matrix. This one here, I've got this an example because it's a matrix plus itself. So what we'd actually get is 6, 10, 4, 0. But what we could do is, just like in regular maths, if you do 2 plus 2, that's the same as 2 times 2. Or if you do 3 plus 3, that's the same as 2 times 3. Or if you do a plus a, that's the same as 2a. In this case, we can actually write that as being equal to 2 times 3, 5, 2, 0. And this is what we would call a scalar multiplication, and we'll explore that in a little bit more detail on the next page. And here we can see we've got an example with some negatives thrown in, we've got some irrationals kicking around, and we've got a fractional number there. And we could just execute this. This is with regular math. So minus 3 minus 1 is minus 4. 1 minus minus 4, be careful because you're subtracting a negative, so you're actually adding it. So that becomes 5. Okay, just be careful with your negatives. So easy to make a sign error. Root 2 minus root 2, well, that's 0. Okay, that gets cancelled out. And then 3 halves minus 5 is going to be minus 7 halves. And that's the answer. Okay. Some additional properties. Addition in matrices is commutative. That's a fancy word for meaning that a plus b is the same as b plus a. Okay, that's the same as regular maths. Additional property, another additional property, sorry, is that it's associative. Again, true in regular maths, regular algebra, so you can follow this. But if you have 3 added together, then it doesn't matter which you do first. You can do the second 2 first, or you can do the first 2 first. But once you evaluate it, you'll end up with exactly the same answer. And they're fairly easy to prove. If you want to go ahead and prove it, prove it for a particular size, for example, maybe. So maybe call matrix A, A1, A2, A3, A4, B, so on, and C. And then follow through with the algebra, and you'll prove that the associative and the commutative properties are true for any A, B, and C. That obviously proves it for that size, but hopefully that will convince you enough. And then on to the trickiest part of the lesson, matrix multiplication. So we've looked very briefly at scalar multiplication already. So 2a is just a plus a. Okay, so it's exactly what you'd expect. More generally, if you have k times a, then what you would do is, well, let's say a is the matrix A1, A2, A3, A4. Then you would take k as the scalar multiplier, so whatever number it is, and you can bring it into each element into the matrix. So KA1, KA2, KA3, and KA4. As a general example, let's have a look at a numerical example. If we have 5 multiplied by, let's go with 1, 0, 2, 4, then the answer to this would be 5, 0, 10, 20. Because I'm taking 5 into the matrix and I'm multiplying every element within the matrix by that scalar multiplier. And that's the scalar multiplication. Okay, that's a simple one. Matrix multiplication, this is where it gets a bit tricky. So you must pay attention to this part of the video. And if you need to pause and rewind, then please do that. I'll also be referring you to the textbook as well, as that explains it pretty well too. Okay. So matrix multiplication. So we're going to have 2 matrices, and we're going to let A be an n by m matrix. Okay, so we've got n rows and m columns. And we're going to let B be a p by q matrix, i.e. that's got p rows and q columns. To multiply those 2 matrices together, it's only possible if m and p are the same number. The output matrix will then be a size of n by q. Okay. So A times B is only possible if m equals p. Okay, that's the number of columns of the first matrix is equal to the number of rows of the second, and the output matrix will be of size n by q. Okay. Why? Why is that even a thing? Well, let's have a look. So here we have an example. This one is possible. We've got, first of all, 2 by 3 matrix, and I'm going to times it by this 3 by 2 matrix. And we can see that the number of columns of the first matrix is equal to the number of rows of the second matrix. So because these 2 numbers are equal, it means this matrix multiplication is possible. The output matrix will be of size 2 by 2. Okay, 2 by 2. So that's our output size. Okay, well, let's just explore how we're going to calculate this. Well, to get this element here, okay, that's the top left element, what we're going to do is we're going to take the top row and the left column. This may feel real bizarre to do this, but this is exactly how matrix multiplication is done, so you just need to go with it for now. So the top row and the left column, you always take the row from the first matrix and the column from the second. The top row and the left column will give you the top row left column element. Okay, so the top row from the first matrix, the left column from the second, will give you the top row left column from in the answer matrix. And the way we calculate it, this is why these 2 numbers need to be the same, is we take each element in this row, we times it by its corresponding element in this column, and then we add them together. It's what's called a sum product. So in this case, the 2 gets matched with the 1, the 4 gets matched with the 0, and the 3 gets matched with the 1. So this element up here will become 2 times 1, plus 4 times 0, plus 3 times 1. And that answer is 5. So that number there is a 5. Okay, and that gives you that element. And then we just repeat exactly that for the other 3 positions. So top row right column will give you the top row right column. Bottom row left column will give you bottom row left column, and bottom row right column will give you bottom row right column. Okay, that's fairly straightforward. So I'm going to circle these ones as well. Okay, so I've circled in green. We're still going to stick with the top row. This time I'm moving to the right column, so it's going to be this element up here. And to calculate it, it's 2 times 2 plus 4 times 3 plus 3 times 1. And that's going to give you 4 plus 12 is 16 plus 3 is 19. So that element there is 19. Okay, and do exactly the same for the other 2. I'm not going to circle these because it'll get very messy. So it's going to be 4 plus 0 plus 3, that's a 7. And then this one here is going to be 8 plus 3 is 11 plus 3 is 14. So that's a 14. So this matrix times this matrix is this matrix. Okay, and that is exactly how we would go about carrying it out. Okay, I hope that makes sense. If you need to rewatch that, then please do. I've got another example, and in fact what I've done here is I've taken exactly the same 2 matrices, but I've swapped the order. Now with matrix multiplication, we lose what we call the commutative property. The commutative property means that you can swap the order of the parts of it, and the answer will be the same. Okay, so we've lost that property. So in matrix algebra, A times B is not necessarily the same as B times A. So it matters which order you do it. And this is a prime example because up here we had matrix A times by matrix B gave you a 2 by 2 matrix. You swap the order of those 2 matrices. Well, we're now going to get a 3 by 3 matrix. Okay, and there's no way that a 2 by 2 matrix can ever be the same as a 3 by 3 matrix. They are 2 very different matrices. Okay, so this is just one example which proves that matrix multiplication is non-commutative. Okay, it matters which order you multiply. Saying that, the process is exactly the same. So we've got number 2 here and number 2 here. So because these 2 numbers are the same, it means that this product is possible, and the output matrix is going to be 3 by 3. And what we're going to do is we're going to have top row by left column, and that will give you this element up here. So that's going to be 2 plus 8, so that's going to be a 10. And then we could do the top row multiplied by the second column, and that would be 4 plus 2, which is 6. And then we could do top row multiplied by the third column, and that will give you 3 plus 6, which is 9. Okay. And we can continue that. Do the second row, that's going to be just 3 times 4, which is 12, because the zeros are going to cancel the top row. 3 times 1 is 3. 3 times 3 is 9. And the bottom row, well, it's going to be 1 times that plus 1 times that. So essentially just adding the columns. So it's going to be 6, 5, 6. So this times that is actually this matrix, which is very different to the matrix we had up here earlier. Okay, so swapping the 2 matrices can change the answer drastically. And finally, just to finish this lesson, we're just going to wrap up with this question here. We've got 3 matrices that are defined for us in the question, and we just need to calculate these 8 matrices if possible. Okay, so first of all, I think it's useful to just write down the size of these matrices. So this has 2 rows and 1 column, so therefore it's a 2 by 1 matrix. This is a 2 by 2 matrix, and this is a 1 by 2 matrix. Okay, it's got 1 row, 2 columns. So if I want to calculate AB, that's going to be this times this. Well, unfortunately, the second number in A does not match the first number in B. Therefore, that matrix product is not possible. So I'm just going to write an X in there. That answer is not possible. Okay, well, I'm going to swap them around though and do B times A. Well, that should be possible because the second number in B is equal to the first number in A. So that's going to become 2, 3, 0, 1 multiplied by 4, 5. And this is possible. It's going to give me 8 plus 15, which is 23. And then it's going to give me 0 plus 5, which is 5. So that's the answer to that one. Okay, so that matrix product was possible. AC. Okay, so we're going to have 2 by 1 times a 1 by 2. The ones match, so therefore this is possible. So let's carry it out. So we're going to have 4, 5 multiplied by minus 1, 2. The output of this is going to be 2 by 2. It's a bit odd, this one, but just stick with that rule which I gave you. So the row of the top multiplied by the column of the second, so top row of the first by left column of the second, is going to give you minus 4. Then I've got 4 times 2, which is 8. 5 times minus 1, which is minus 5. And 5 times 2, which is 10. Okay. There's only one element in the rows and the columns, so that might throw you a little bit on this one, but that matrix product is possible. Swap them around. If I've got C times A, well, that's going to be a 1 by 2 matrix times a 2 by 1 matrix, and the 2's match up, so therefore this is possible. So minus 1, 2 multiplied by 4, 5, and the output matrix is going to be 1 by 1. It will look like just a number, but you should still have it in round bracket.